process, we covered the half wave rectifier. So we are going to just tackle a numerical example, which is a very easy example, but it's going to illustrate the basic principles of workings of the how to deal with problems on the half wave rectifier. So let us quickly do it. Again, I don't like this polarity business in this book, but anyway, we have to stick to it. So this is Vs sine omega t, and the resistance, and this is my diode. Okay, the coordinates are not. Oh, it can't be easily seen like this. Okay, but here it's very difficult. Okay, that draw. Okay, so here is my VB plus minus, and here is my ID. Okay, now so what is happening? We are given VB is 12 volt. So VB is 12 volt. VB is, yeah, and we are given R is as oops, it's different here. R is 100 ohm, and V gamma here is 0.6 volts. So and Vs here, this is 24 sine omega t. Okay, and we are supposed to find number one, the peak diode current. Can anybody guess quickly? What should be the peak diode current? It is not very difficult. What should be the peak diode current? This is a voltage source. This is a 24 sine omega t. So the maximum voltage in the diode is what? So here the maximum voltage is 24. So the peak diode current will be 24, simple. 24 minus what is this voltage source is opposing. So 24 minus VB minus V gamma, because this there's a drop of V gamma here. So plus minus. So 24 minus VB minus V gamma divided by R. As simple as that. The maximum voltage is 24. So the peak diode current is 24 minus 12 minus 0.6 divided by 100. Okay, so that comes out to be 114 milliamps. Okay, so this is Vs minus Vb minus V gamma by R. Okay, there's no doubt about that. Now, second, the maximum reverse bias diode voltage. Max reverse bias diode voltage. What it will be? Any guess? For the reverse bias, okay, that means what? The no current is conducting. There is no current, so the voltage at this point, the voltage is 12 volt. Anyway, if the current even the diode is conducting, the voltage at this point is 12 volt, and the voltage at this point at the peak reverse bias, no, the diode is not conducting. That means there is no drop across R. There is no drop across this resistance. So the voltage at this point should be for the maximum reverse bias voltage, it will be minus 24. So here it is plus 12, there it is minus 24. So 12 minus 24, so 12 plus 24. Okay, easy. So that is Vs plus Vb, 24 plus 12, whatever that is, 36 volt. Now the diode conduction cycle, obviously when you know, we know that the diode is going to be going to be on for half of the cycle and going to be off for half of the cycle. So we have the diode conduction cycle like this. So the diode is going to be conducting for this period of time. So this is omega t1. So this is omega t1, and that is omega t2. Okay, this is omega t1 and that is omega t2. Omega t1 and omega t2. Okay, now so my diode conduction cycle will be what? When the diode is just starting to conduct, when the diode is just starting to conduct, let me just go to the. So when the diode is just starting to conduct, the voltage at this point, will be 12 plus 0.6. Suppose this voltage is steadily increasing from 0. The AC source is steadily increasing from 0. Here. Okay. The moment the voltage at this point reaches 12 plus 0.6. The voltage at this point reaches 12 plus 0.6. The diode just starts to conduct. So at that point, there is almost no drop across R. So the current is 0 because the diode is just starting to conduct. So 12.6. So 24 sine omega t1, when it reaches just 12.6, the diode will just start to conduct. Okay, so therefore we write for the diode conduction cycle, (24) sine omega t1 equal to 12.6. Okay, note that the drop across R is just 0 because the diode has just started to conduct. Moment before, the diode was not conducting, so there will be no drop across R. So the diode conduction cycle is 24 sine this point. Okay, sorry, this point. So 24 sine omega t1 is 12.6. So sine omega t1 will be, sorry, omega t1 will be sine inverse that. Which works out to be 31.7. And therefore omega t2 by symmetry should be 180 minus 31.7. Definitely. So that will be equal to 148.3. So this demarcates this period. So therefore the diode conduction cycle, the percentage time of the diode conduction cycle will be 148.3 divided by 360. Oh, sorry, 148.3 minus 31.7. Omega t2 minus omega t1 divided by 360, the entire conduction cycle from here to here. That is 360 degree. So this entire period is 360 degree. So from here to there, 360. So 148.3 minus 31.7 by 148.3 minus 31.7 by 360, which works out to be 32.4%. So this is the diode conduction cycle. Okay, very easy, not very difficult at all, but you have to practice. As I told you, if you don't practice, even easy things will appear difficult in the examination because you have to tackle a lot of problems. So now let us go to full wave rectification. Again, it is you have met with part of this during your previous school years probably. So we have a transformer again. As I told you, this is to prevent the risk of electric shock for the circuits down below, which are full wave rectified, which are being fed by the full wave rectifier. So this and this and so the output is taken across this. The output is taken across this. So this is V0. This is V0. So what is going to happen? Again, very simple to understand. Almost does not need much explanation. So you see, this is the positive side. This is the negative part. This is the positive part, negative part, positive part, negative part. Okay. So what is going to happen? Almost you can explain. So what is going to happen when this voltage is positive? Let us give this voltage name Vi, and let's call this voltage as Vs. Let's call this voltage as Vs. So during the positive half cycle of Vi, when this voltage, the voltage here is positive, this diode is going to conduct. Let's name this diode D1. Let's name this diode D2. When D1 conducts, then the voltage across this resistance, will be of this polarity, because D1 conducts and the current returns here because this is the conduction path. Similarly, when we have the other cycle, when Vi changes polarity, then this voltage Vs changes polarity. So then diode D2 starts to conduct. And if diode D2 starts to conduct and D1 is turned off, during the positive half cycle of Vi, D1 is on, D2 is off. During when Vi is positive half cycle. When during the negative half cycle, D2 is on, D1 is off. Vi negative half cycle. D2 is on and D1 is off. And when D2 is on, the current will follow the same path here, like this. So the voltage polarity across R is the same regardless of the polarity of Vs. Simple to understand. But there will be a drop of V gamma, because in either cycle there will be a drop of V gamma across this diode D1 or across this diode D2. Depends on which is on. So therefore, the voltage across R in the positive half cycle will be Vs minus V gamma. because we have a voltage Vs here, and minus V gamma, the V gamma drop across the diode D1, and then that will appear across the resistance R. When we are in the negative half cycle, the voltage at this point is minus Vs, because the polarity of Vs has changed sign. So it will be minus Vs. The voltage across R will be minus Vs minus V gamma. Minus Vs minus V gamma. So this will be V0. And this is also V0. So what do we have for the waveform? If this is my waveform, as we all know, if this is my input waveform, Vi or Vs, you can say this is as Vs. So here we will have my output waveform. If I draw the reverse of the input waveform here, sorry, output waveform is not properly drawn. Oops, here. Let me draw it afresh. Okay. Continue here. So then my input waveform will be like this, and this is my output waveform is in red, and this is my okay. So there will be a lag of the, not a lag but a offset. So this is the blue is the input waveform Vs, and the red is the output waveform V0. The difference between the thing which has to be understood is that Vs equal to V0 is Vs minus V gamma. So therefore this distance from here to here, this distance will be V gamma. So this is V versus time. So this is it is called a full wave rectifier with a center tap transformer. So let us write full wave rectifier with center tap transformer. Okay. Why center tap transformer? Because this point is grounded. Because of this, the center of the transformer here, it is grounded. It is connected to ground. That is why it is called center tap transformer. Okay, and therefore this is one type of circuit for the full wave rectifier. Now let us go to another kind of circuit, which is called the bridge rectifier, the full wave bridge rectifier. And here we will have, instead of 2 diodes, here we'll have 4 diodes. Let us draw it in a bigger way so that it is easier to understand. Let us draw it in black. Okay, again, the circuit operation is very simple to understand, not difficult at all. What is happening? VI here, VS here, sorry, VS here. Okay, let's name these diodes D1, D2, D3, and D4. So when Vs is positive, during the positive half cycle of Vs, positive half cycle of Vi or Vs, what is going to happen? Diode D1 and diode D2 is going to conduct. The current is going to flow in this manner. So this will be forward biased and this will be forward biased. Diode D1 and D2 will be forward biased. So here D1 and D2 will be forward biased and D3 and D4 will be reverse biased. So this is your resistance R. And when Vs changes polarity, the opposite thing will happen. The complementary diodes will be conducting. So diode D3 and D4 will be conducting. So when Vs changes polarity or the negative half cycle of Vs, diode D3 and D4 will be forward biased and diode D1 and D2 will be reverse biased. So therefore, the current is going to conduct again in this fashion during the negative half cycle. So therefore, the current through R follows the same path. The drop across R is of the same polarity, regardless of the polarity of Vs. Sorry, there is a small omission here, has been a small omission. This part of R is grounded. So this is grounded. So this side of R, this point is grounded. But the center is not grounded. So this is not grounded. Okay, so this has to be remembered that for the bridge rectifier, one side of R is grounded. This is a big difference between the center tap transformer. Whence the name is different. Whence the name bridge rectifier and the name center tap transformer. That is, the center of the transformer is not grounded here. One side of R is grounded. Okay. The other difference which you see is that in the case of the circuit with the center tap transformer, what did we have? The voltage V naught was Vs minus V gamma, or minus Vs minus V gamma. There was only one diode drop involved. But in this case, V naught is equal to Vs minus 2 V gamma. So if I draw the circuit, if I draw the voltage versus current characteristic, if this is my input waveform and this is my, sorry, minus Vs. So the solid line is plus Vs. So therefore, this will be my output voltage V naught, and Vs minus V naught, this gap will be twice V gamma. This is important to understand. There are 2 diode drops. So we need 4 diodes in this case to achieve full wave operation. But there, for the circuit with the center tap transformer, we needed 2 diodes. So on the face of it, we will we see that, okay, this we have to purchase 4 diodes. But several advantages are there for the bridge rectifier, which far outweigh the use of 4 diodes. And that is explicitly borne out by the following example. We are going to see why the bridge rectifier is advantageous over the circuit with the center tap transformer or with the previous circuit. Let us work out a simple example. So assume an input source 120 volt RMS. From a 60 hertz source. The desired output voltage V0 is 9 volt. The diode cut-in voltage is assumed at 0.7 volt. Let us compare the performance of the center tap transformer. How much is the peak inverse voltage required for the center tap transformer configuration, and the number of turns required. So we see the Vs max, the maximum voltage, is V0. We have already covered this, that is V0 max plus V gamma. Because V0 is Vs minus V gamma, so that is 9.7 volt. And the RMS value will be, because this is 120 volt RMS, so we have to convert this to RMS in order to find the turns ratio. In order to find the turns ratio, we have to convert this to RMS, because this is in RMS, this is in peak voltage. So we have to find out Vs RMS, that is 9 volt by root 2. Vmax by root 2 is VRMS. So that works out to be 6.86 volt. And therefore, the turns ratio N1 by N2, here the number of turns is N1, here the number of turns is N2. The turns ratio N1 by N2, sorry. Where we go? For this one, here is N1, Here is N2. From here to here is N2. From here to here is N2. So this part is N2 from here to here, and that part is N2 from here to here. So you see that if I go here, N1 by N2 is how much? 120 by, because we are going to Vs max. Vs max. So Vs max is where? Vs max is from here to here, from this point to this point. So N2 is from here to here. Here is N2, number of turns. So therefore N1 by N2 is 120 by, oops,
Sir,
it is 120 by 6.86, and that is about 17.5. Yes, somebody of you had a question.
sir, it is Vs RMS equals to 9.7 by root 2, right?
That's right. That's right. Sorry. Absolutely. Thanks. It is 9.7 by root 2, right? You're right. It's 9.7 by root 2. So this is this. Right. So here you see that 17.5. For the bridge circuit, however, what do we see? Bridge, rectifier. So what do we see? Vs max will be, as we discussed, V0 plus 2 V gamma. So V0 max plus 2 V gamma, and that is 9 plus 2 into 0.7, which works out to be 10.4 volt. And therefore, if I compute the the corresponding RMS, it will be Vs RMS will be 10.4 divided by root 2, which works out to be 7.35 volt. Now you compute N1 by N2. So it is 120 by 7.35, which turns out to be 16.3 about. So you see now that twice the number, this number is the same, almost the same. 17.5 is almost the same as 16.3. So almost twice the number of turns are needed for the circuit with the center tap transformer. That is one disadvantage of the center tap transformer, or that is one advantage of the full wave bridge rectifier over the center tap transformer. That it requires, the bridge rectifier requires almost half the turns, half the number of turns corresponding to the, or compared to the circuit with the center tap transformer. Now let us find out what is the peak inverse voltage. Can any of you say? Let us go back to the previous slide. Here, what is the peak inverse voltage? Let us suppose the diode D1 is on. So what is the voltage at this point? The voltage at this point, when diode D1 is on, is Vs minus V gamma. This point is the same as this point. Our main intention is to look at this diode now, diode D2. When diode D1 is on, the voltage in the inside of D2, which is at this point, is Vs minus V gamma. What is the voltage here? the voltage here, because it is going through the reverse bias, it is minus Vs. Because the voltage here is 0. The voltage here is 0. It is grounded. The voltage at this point is ground. So the voltage at this point will be minus Vs. It is below 0. So this drop is Vs. Therefore, the voltage on the P side of D2 will be minus Vs. And therefore, what is the PIV of the diode? D2. The peak inverse voltage, what the diode D2 has to tolerate under the maximum reverse bias, it will be Vs minus V gamma minus of minus Vs. Vs minus V gamma on the N side of D2 and minus Vs on the P side of D2, and this works out to be twice Vs minus V gamma. And if I plug in the values, twice Vs minus V gamma is 2 into 9.7. 9.7 was Vs max, the maximum voltage, because we are finding the peak inverse voltage. Follow this word, peak, the maximum reverse bias voltage. So we have to take the maximum forward bias voltage, 9.7, the peak minus point whatever, 0.6 or 0.7. 0.7. V gamma was 0.7.
Sir, which side is minus Vs and which side is Vs minus V gamma?
Again, look at this. Again, wait, let me just finish it. I will repeat this argument again. So 2 Vs minus V gamma, and that is works out to be 18.7. Okay, now you see, when you have to find out the peak inverse voltage, what are we comparing? We are comparing the peak inverse voltage of the diode which is under reverse bias condition. So let us assume that diode D1 is on. This diode is on. If this diode is on, if diode D1 is on, the voltage here, the N side of D1, it is Vs minus V gamma. This voltage, Vs minus V gamma. This voltage is the same as this voltage, the voltage here. So this is on the N side of D2 as well, Vs minus V gamma. So we have to find out the voltage across D2 when Vs is maximum. That is the worst voltage which D2 has to tolerate without breakdown. This is the worst voltage which D2 has to tolerate without breakdown. So therefore, in this case, when D2 is like this, then you the voltage on the positive side, the voltage on the positive side of D2 is what? The voltage on the P side of D1 is plus Vs. This point is ground. Of the transformer is at ground. So therefore, the voltage here when the peak appears is minus Vs. So the voltage on the P side of D2 here is minus Vs. So therefore, the PD across D2 is Vs minus V gamma minus of minus Vs, which works out to be 2 Vs minus V gamma. Simple. Okay. What happens now to the full wave bridge rectifier? When D1 is forward biased and D2 is forward biased, consider this. Now you question what is the PD across D3? What is the potential difference across the terminals of D3 when it is reverse biased? Under the peak reverse bias condition, you see that the one side of D3 is at 0. Here, one side of D3 is at 0. We need to find out what is the voltage here. But please do not make the mistake that it is plus Vs. Because in this circuit, this is not the ground. This is not ground. You have to remember. This is not ground. Ground is here. Ground is here. So if I have to find out the voltage here, it is not plus Vs because the ground of the circuit is here. So in order to find out what is the voltage at this point X, we need to go from here. From here, when D2 is conducting, the potential drop is the voltage here is minus V gamma because D2 is conducting. And from here to here, if I have to jump, it will be Vs. So the total voltage here will be Vs minus V gamma, or more aptly minus V gamma plus Vs. First of all, there is a minus V gamma and there is a plus Vs. That is the voltage at the point X. Therefore, the potential difference across diode D3 will be Vs minus V gamma minus 0. Therefore, the peak inverse voltage PIV, which is VR max, will be Vs max minus V gamma, and that is 10.4 minus 0.7, which is 9.7 volt. That is for the bridge rectifier. Compare this with the full wave rectifier, the center tap transformer. PIV was VR max. Now you compare these two numbers. So you see that the PIV of the diodes for the center tap transformer circuit is almost double. It is almost double than the PIV for the diodes with the, for the case of the bridge rectifier. Therefore, the diodes for the used for the center tap transformer has to tolerate a much larger reverse bias without breakdown, almost double the voltage without breakdown compared to the diodes in the used for the full wave bridge rectifier. In addition, as we see that only half the number of turns are needed for the circuit with the bridge rectifier. Okay, so these are the two important advantages of the bridge rectifier over the one with the center tap configuration. Now let us go to the finding out the ripple capacitance, computing the ripple and finding out the filter capacitance needed for the to control the ripple. So now you see that the kind of voltage we saw, that this kind of a waveform which we obtained for the, like for the full wave rectification, in most of the times it is no good. We need for a power supply voltage, we need a steady output like this, not a voltage like this. So this is desired, this is undesired, so to say. I mean, just from a common sense perspective. So what do? We have the diode, which is fed by your AC source. Again, this is a source like this. And we have a filter capacitance. So what happens as a result of this? Very simple again. When this diode reaches the peak voltage, the capacitance charges up to the peak voltage. So in this half of the cycle, the capacitance charges. The capacitance charges up here, up till here. Now the input voltage starts to drop. When the input voltage starts to drop, the capacitor voltage will also drop. But the capacitor, in order for the capacitor voltage to drop, the capacitor has to discharge. But it has no discharge path to this, because the current through the diode cannot flow from the N to the P junction. So the capacitor does not have a discharge path to this. The only discharge path of the capacitor is here. So the capacitance will discharge to R. And if I design the circuit such that the RC time constant is very high, if I design the circuit such that the RC time constant is very high, then the capacitor will discharge very slow here. Again, when the capacitor voltage falls, and when the diode voltage here becomes greater than the capacitor voltage there, again the diode will conduct. And when the diode conducts, again the capacitor will charge. So when the diode conducts, the capacitor charges up to here. The moment the voltage starts to fall, the capacitor again discharges to its RC time constant here. So the output voltage is this one, this one, this one, this one, like that. So this voltage, again this one, like that. So this voltage is called ripple. We wanted this voltage, but we got something like, this is ideal, this is what we want, this is what we want, this is what we got. So the difference, the lower the ripple, the better my circuit. So this is the ripple voltage. So let us then compute what is the value of the filter capacitance needed in order to get a particular ripple voltage. For that, just let us draw the waveform in a better way. And then what is happening is, let us draw it in red. So we mark this as t prime, the forward time, and this time we mark it as capital T prime. And this is the period, time period. And this is, as I wrote down before, this is V gamma. VR, sorry, not V ripple voltage. V ripple. So this is what is happening. So let us describe this by a simple mathematical equation, because we know the equation of the discharge path, which is this path. This path. So here, this is my V0. This is my V0. This is my time. This is the Vmax. And the lowest voltage, this is VL. So VR is equal to Vm minus VL. Okay, so VR equal to Vm minus VL. So we have V0, sorry, let's simply write down these equations. V0t is equal to Vm e to the power minus t by t prime by tau. V0t is Vm e to the, all I'm writing is the equation of this path. So VT0t is Vm, the maximum voltage, e to the power minus t prime by RC by tau, which is equal to Vm e to the power minus t prime by RC. Now, if I have to find out VL, we know that VL is the minimum voltage. So that is equal to e to the power minus t prime by RC, because the time taken to reach the minimum voltage is t prime here. So the voltage VL falls here, and the time elapsed is capital T prime here. So VL is Vm e to the power minus t prime by RC, and therefore VR equal to Vm minus VL is Vm 1 minus e to the power minus t prime by RC. Now I told you that the RC time constant is designed to be very large. So if the RC time constant is very large, that is t prime is very much less than RC. Therefore, e to the power minus t prime by RC can be approximated as 1 minus t prime by RC by the exponential rule, and therefore V ripple becomes, my V ripple becomes Vm t prime by RC, substituting here to there. Now, the problem is t prime will depend on RC. It is not very easy to find out t prime, because t prime will depend on RC. The more the value of RC, the more the value will be T prime, because this voltage will go discharge slowly. As RC becomes more, this voltage becomes more. This time becomes, sorry, as RC becomes more, this time T prime, capital T prime, this time becomes more. So T prime depends on RC, capital T prime depends on RC. So this is not easy to solve, because T prime, capital T prime will depend on RC. For a first order approximation, we assume what is desired. So T prime can be assumed to be equal to TP, because that is desired for us. It is almost, RC is so large, so we assume that RC is so large that T prime is almost equal to TP, which is desired. So RC is very large. Okay, so almost no, the discharge is almost nil. So therefore T prime is almost equal to TP, is RC is very large. So for a full wave rectifier, TP is 1 by 2f, because it is half the signal period. What was TP? Here. Here, it is half the signal period. Okay, this is a full wave rectifier, so it is half the signal period. The full signal period is from here to here. Okay, so here to here, if there is another wave like here, so this corresponds to half the signal period, capital TP. So TP is 1 by twice f. So therefore f is 1 by 2 TP. For a full, this is for a full wave rectifier. So therefore, substituting this instead of f here, instead of TP here, so VR is almost equal to VM TP by RC from here, using this one and this one, and that is equal to VM by twice f RC, because
Excuse me, sir.
TP is 1 by twice f. Okay,
So we
VM,
have another class.
oh, okay.
It's 11:1.
Yeah, so I'm just 1 minute to conclude. So VM is 1 by twice f RC. So you see, this gives the relationship to find out the value of the required capacitance C once you are given the value of the ripple voltage. If I'm given the ripple voltage, using this relationship, I can compute the value of C. Okay. Okay, let's stop here. Wait to download the attendance. Okay, you can leave. I'm stopping the class.